What I'm going to talk to you about today is water quality trends as related to agricultural best management practices in the Choptank watershed. So it's the watershed just north of the Nanticoke. So the Choptank Basin, so we're familiar with it in that its dominant land use is agriculture and then forest and development. So very similar characteristics to the Nanticoke watershed. What I want you to gather from this is that land use is directly related to the water quality, in that what we do on the land will impact how healthy our waterways are. And I want to show you some data to back that up. We're first going to take a look at down near the mouth of the Chesapeake Bay, DNR Estuary Station ET 5.2. So first graph, we have on the top panel annual average chlorophyll A, and on the bottom, summer bottom dissolved oxygen. What I want you to understand from this graph is that a trend started to switch in the year 2005 with a decrease in that chlorophyll A and then an increase in bottom oxygen. So what this indicates is that water quality is improving in the lower part of the Choptank River, but it's still not that great. Moving up the estuary and into the headwaters of the Choptank River at this Greensboro USGS gauging station, the trend is continuing upward for those nitrogen values in the top panel and then those phosphorus values in the bottom panel. So we're not actually seeing an improvement upstream. And we're wondering, well, why is that happening? And then what can we do on the land to improve that water quality? So that brings us to this project that I'm working on at Horn Point Lab in Cambridge, and we're hypothesizing on this research study that if we improved agricultural best management practices and increased the number of those practices on the land within a few small watersheds near that Greensboro station, then we will actually see an improvement in water quality. So what are those best management practices that we're looking at? It's some of these and more, some of which Tim talked about already. And best management practices, as you know, are supposed to reduce those nutrients, nitrogen, phosphorus, and sediment, relating back to that Chesapeake Bay program, TMDL. So, talking about my project, or our project specifically, we're looking at these 4 small watersheds. They're up there in tan, here we go, right here. And that Greensboro location is that black dot. We have 4 of those watersheds, and this is a collaborative project funded by the National Science Foundation. We were awarded a grant in 2013 just over $1 million to do a 5-year project. And we selected those 4 watersheds in the upper basin because of their similarity in size and general watershed characteristics. One of those is a control, and 3 additional ones are experimental watersheds. And we also have an outside control right here, actually located in the Marshy Hope. It's a very small tributary to the larger tributary of the Marshy Hope. And I'll actually be visiting it later today to collect a sample. But I unfortunately don't have that data set with us today, but I can show you it later. So, our project was 5 years. We used the first 2 years as our baseline data collection, so we were sampling at over 80 sites throughout those 4 watersheds to get a general idea of what their water quality looked like before we did any experimental modification, which consisted of encouraging the application of best management practices. So in order to do that, we really worked with a lot of farmers, including UMD Extension in the county, in Caroline County, to make these contacts with existing farmers and then understand a bit more about where they were coming from with their installation of best management practices and what we could do to encourage them. So going back to our funding, we received funding from NSF under their Coastal SEAS program, SEAS standing for Science, Engineering, Education, and Sustainability. Sustainability, when you think of that as a term, you think about economics. You also think about the impact of sustainability on the people, and then in this project, the planet. So we're accomplishing the 3 tiers, or the 3 definitions of sustainability through water quality monitoring, social surveys, and then we also did a cost-benefit analysis of best management practices. So with every single participant farm owner and landowner who was willing to complete a survey gave us that data, and we have some information on various impediments that those farmers identified as, why they wouldn't necessarily put a best management practice down or not. So, but this talk is going to focus a bit more on the water quality data. So at those 80 sampling sites in those 4 watersheds, we broke it down into 3 spatial scales: the watershed outlet, the Meso scale, or sub-watershed scale. So we broke those watersheds down even further and sampled on some of the smaller tributaries. And then on the field scale, where we were sampling things like groundwater wells that we installed, so it's not drinking water. They're small plastic pipes that we drill into the ground, or tile lines, as Tim talked about. So what we found in the first 2 years of our project, so 2013 and 2014, was there were already so many best management practices installed in these 4 watersheds, which was mind-blowing to us and really eye-opening because we did not know much about agronomy at that point, and we still are learning a lot. So what did those best management practices look like? Some of this data was collected through field observations, also looking at aerial imagery of the area, and talking with our farmers about what practices have been put down, and then, of course, coordinating with the Maryland Department of Agriculture to get some of those numbers. So with all that in mind, considering the social surveys, we found that the reason that the maximum number of best management practices didn't go down on the land was, number one, out-of-pocket expense. So that 87.5% cost share, that still leaves 12.5% of funding that the farmer has to cover out of pocket unless you apply for other funding sources to try to get that cost covered. And that's what we did as a research group. We found that, well, if we can get some additional funding and partnering with organizations like Shore Rivers for a NIFWIF grant, or with the Hughes Agroecology Center to cover that 12.5%, then that would be at no cost to the farmer, and then all they would have to do is say yes, right? In some cases, that's exactly the impediment that they needed taken away in order to put a practice in place. So with some more money, we were able to get some more best management practices on the ground. So during our experimental years, 2015 through 2018, and this year too, we were able to help out indirectly or directly with the installation of these practices and more. These are only the ones that I know of as a project. So moving on to transition to some of the data, I'm going to specifically look at an area of where there's 2 groundwater wells that we know only received a lot of cover crop in 2015, 2016, 2017, and the fall of 2018. So this is our first and only field example looking at 2 groundwater wells. We know there was no cover crop planted in this time frame for the first 2 years of study because of our communications with the farmer. But we know that the ag area immediately surrounding those 2 wells received upwards of 95% coverage of cover crop. So our first data graph, the top panel is nitrate in parts per million, or you could equivalent or have it equal milligrams per liter, but what I want you to understand is that it's very high. It's over 15 parts per million. And phosphorus is in the lower panel, and I want you to understand that it's not very high at all, so it's almost, not a concern in this area for these 2 wells. So as time went on, we had those applications of cover crop in the fall, and I didn't put the one down for 2018, and we saw a decrease in nitrogen in that top panel, which was significant. However, as the time went on, it came right back up, and we were scratching our heads, well, why did this happen? Are the cover crops suddenly not working? Well, we do know that the farmer did apply some manure, which is not at all a bad thing. They're just doing what they're, to get to their bottom line and put that manure somewhere on the landscape as they do with their farmer and nutrient management plans. So we're just trying to understand what's happening with our data set in order to more accurately interpret it. Another thing that we noticed was there was this sort of cyclic effect in our data set. We're wondering, oh, well, maybe the cover crops didn't actually do anything, and then it's just all related to weather or land use and management impacts, or everything. So the story that I'm telling here is that this data set shows a convoluted picture of what's happening in the environment, and it's pretty hard to determine a cause and effect. We also know in 2017 and 2018 that it was really wet. Last year we received about 30 inches above average for rainfall, which totaled about 70 inches for this area. So that's something that we have to consider when interpreting our data. Moving on, one scale up to the Meso or sub-watershed scale, I have 3 examples. So the first, you've seen this before, what we knew was on the ground in 2013 and 2014, and then what we helped put down 2015 through 2019, which is a lot. Some of this was done with shore rivers. And then what was also present through all of the years. So looking at this Meso station, I've covered up most of the graph here. You can see in the early years this is nitrogen, phosphorus, and then total suspended solids. Nitrogen's moderately high, phosphorus is low, and then total suspended solids are pretty low as well. But as the time goes on, what I want you to observe for nitrogen in particular is that after some successive cover crop application, nitrogen went down by a factor of 50%, and that's a mean average that I have circled there. So cover crop we determined was a contributing factor, but maybe not the only factor in this result here. And there was no significant change for the bottom 2 panels. Moving forward with our second Meso example, there's this site in one of our other experimental watersheds that did have some cover crop on in the early years, but only received more, and then always had some other best management practices on the ground. So there's, again, more practices that are interacting and making this complicated. So you can see in the early years, similar trends, starting with nitrogen, phosphorus, and total suspended solids, but nothing significant happened over the same time period, but this area has had a lot of BMPs down. So we have some mixed results here. And third, this site, we know of no additions in these 2 time periods, but there was potential for some to have gone on, just not to our knowledge. Go. Oh, there we go. Oh, jumping ahead. Okay. Well, now you can see, so base flow nitrogen started up pretty high and only increased. So we're wondering, oh, okay, well, what's happening in the landscape here for this to have a positive or a positive trend in nitrogen, but nothing happening with phosphorus or suspended solids. So in summary, we had about 22 Meso sites. I showed you 3 examples. For nitrogen, in this half of the graph, most of the sites were unchanging. And same for phosphorus. And that's partially due to the fact that best management practices didn't go down in every single Meso watershed, so we didn't have an impact as a project at every scale, which is pretty hard to accomplish, but amazing that we accomplished so much in some of our watershed areas and still had some positive or some decreases in nitrogen and then a decrease in phosphorus in at least one of our sites. Okay, moving up again to the watershed scale, which is, I think, one of the most interesting scales. So in our first control watershed, this is the one that is in the chop tank. We're starting out with base flow total nitrogen that's pretty high still, but not as high as the experimental watersheds. And I want you to focus kind of on that trend line. It seems to be dipping down and then going back up again, but then it flattens as the time goes on. And I want to point out that the time frame is a bit different from the graphs that I was showing you. So we have it starting around 2003 and then going to the present. This is because we've monitored these watersheds for a longer period of time at the outlets, not the Meso stations. And I'm relating this data to this bottom graph here, which is showing you cover crop coverage, and this is from MDA, from beginning in 2006 and going almost to present. We're awaiting some of the more recent data. And what I wanted to point out with this is, so we see an increase in cover crop, but maybe not, similar decrease in total nitrogen. So I'm not correlating or causing, trying to say that total nitrogen values are affected or related to cover crop, but it could be, again, a contributing factor to what we're seeing at the watershed scale, because cover crops do cover a larger area than most of the other structural best management practices that may only affect maybe 20 acres. This is hundreds of acres that cover crop could go down on. Moving forward to our first experimental watershed of 3, we have increasing total nitrogen and a steep trend line, and that is significant in an increase in our first experimental watershed. But as time goes on, that trend line seems to flatten and trends downward, and we have a significant decrease in total nitrogen. And that we could potentially attribute this latter half of the graph to maybe the effects of our project in encouraging the application of cover crops and other best management practices in this watershed, but we can't say for sure. We've just noticed that that latter half, those few years, are significantly different than the rest of the data set. The same can be said for our second experimental watershed. There's a sharp trend downward in total nitrogen, which is amazing that it's happening that early on. But it still continues to trend downward and seems to steepen just a little bit in the recent years. Our third and last experimental watershed is showing you a very steep increase in total nitrogen that only seems to continue, regardless of what our project is doing. So maybe we're not having an effect of the watershed scale in this watershed, and we potentially attribute that to a variety of different factors. We had low participation in this watershed compared to the other 2 experimental watersheds, and this watershed has a sandier soil profile if you want to get into the technicality of it. But what I want you to understand is total nitrogen is still increasing regardless of what we're doing. So, not all doom and gloom here. There are some positive take-home messages. There were so many best management practices on the ground, and so many that are still being implemented, as you can see with the success of Tim's project, and then many more of the cooperating agencies, both state and federal and county level, in this watershed, in these watersheds. So, and we're seeing both improvements and decreases in water quality due to weather, something that none of us can control, land management, and then a lot more. And I only showed you one example from our field sites. We have over 30 different sites that we sample on the field scale, and we just need to do a little bit more digging in our data to figure out exactly what's going on there. And we are expecting another year of data, but we're only working with about 2 to 3 years of our experimental data, so maybe we haven't seen the change yet. Maybe it's coming, and we just have to wait for more of our data to be analyzed. Thank you so much for listening.
Great, we have a little bit of time. Oh, there you go. So does anyone have any questions for our ag group?
For Ms. Koontz, it looked to me like the most interesting part of your data was that as you went into the later years, especially with nitrogen, the variability shrank. And so to me, what's causing the difference in the yearly change was far greater than anything that happened over the whole 10-year period. The 1 year change. So, and that got less and less and less. So what is causing that yearly difference, and how could it be getting smaller?
That's a very good observation. It worked a second ago. I was just going to say that's a very good observation, and one that I didn't point out myself. I'm not exactly sure what is causing the variability to shrink. Maybe it's our ability to target our monthly sampling to be more focused on true base flow days, where we wait about 3 days after a rainfall event to then get an accurate measure of that base flow period. But potentially it's actually the nitrogen levels are going down because of our ability to manage what's coming off the land a bit better. I would like to know exactly what's going on.
previous board. Oh, Roman?
A question for Erika. Your cover crops were varied over the watershed. So in that one watershed, you had less than 40% cover crops. So what was the deal? Why was cover crops so variable? And the other watershed was up to 80%, I believe. So what was the deal with cover crops, and why did it continually? You had a continual increase. I would think with weather or whatever, you know, you'd have be a lot more variability, but it consistently increased. So could you speak to that a little bit?
I'll target the aspect of your question that talked about the continuous increase of the cover crops. So we believe that's attributed to the success of the MAX program that Maryland supports and actively encourages cover crop to go down on the fields. So in recent years, they've definitely improved their marketing and ability to target farmers through either, you know, University of Maryland Extension or other ag and soil conservation districts. So they've really got that education out there that cover crops do work and that there's funding to cost share it. Regarding the part of your question where cover crop in the control watershed was about 40% at its highest, I'm not entirely sure why cover crops didn't increase to 50, 60, or maybe 70% as you saw in my graphs. We think that maybe some of the farmers in those watersheds are not as supportive of the cover crop program, and it's just a sort of a single choice. It's their ability to pick if they want to put cover crops down or not, and maybe it's just concentrated where there are some farmers up there that don't want to use them. But I can't speak to why they don't want to use them. It's just their choice.
I was going to say, it could also be if you're doing soybeans, you're not going to, generally if you're planting soybeans, you're not going to follow with a cover crop because it's too late to plant. So if someone's doing soybeans after soybeans, they might not have a chance to get it out there. So, and especially these are small watersheds, so it could be the same farmer doing a lot of acres, so he decides to do beans, and most of his acres in that watershed, there's going to be lower cover crops. So it just depends on what's planted out there.
And to comment on that, the cover crops that we paid for, we specifically tried to get them on after soybeans for that reason. It's more common to put them on after corn, at least in this part of the world.